Thank you for taking the time out of your busy schedule. My name is Peter Kesselman. I'm VP of Product Development at TestEquity. This webinar will cover how and why the temperature of your device under test, or DUT, may be different from the air temperature display, the impact on test accuracy and test time, and how to solve this. A live Q&A will follow. Please hold your questions until the end of this presentation. So why do we care about part temperature? There are several reasons why we test products and components at various temperatures. One reason is to see how they will perform at extreme hot or cold temperatures, or to mechanically stress the device by expansion and contraction due to temperature. Another reason is to characterize its performance for every degree of temperature change, such as hertz per degree C, millivolts per degree C, or ohms per degree C, or to test battery life versus temperature. But chambers generally display only the air temperature, which is never exactly the same as the DUT temperature. So let's first talk about how air circulates in the chamber. Chambers have a plenum where the cooling coil, technically called the evaporator, and the heater are located. There is a fan which circulates air in the chamber workspace from the plenum discharge area to the chamber workspace, and then the air returns to the return side of the plenum. You need to have airflow in order to have fast and uniform heat exchange between the workspace, the DUT, and the evaporator or heater. And here you can see the airflow pattern in two different styles of chamber construction with a plenum cover in place. So where does a standard chamber measure temperature? Chambers have a thermocouple or RTD sensor in a high velocity point within the airstream, usually just at the point where the conditioned air enters the workspace from the plenum, or the discharge area, but occasionally located where the air returns to the plenum in the return area, as in the case of our Model 155. The sensor needs to be located in this spot to achieve stable control of air temperature in the chamber. This relates to the spec called control tolerance, referring to the short-term variations measured at the control sensor after stabilization. The number you see for temperature is the value at the air sensor. This is not the DUT temperature. The air control sensor correlates to the DUT temperature, but it's not the DUT temperature. So what about thermal mapping? Some customers map the temperature at 9 points in the chamber, 4 on the top, 4 on the bottom, and 1 in the middle, to make sure the temperature is the same throughout the chamber, typically to within 1 degree C of each other. This is performed in an empty chamber. Unfortunately, it tells you nothing about how long it will take for the temperature at your DUT to stabilize, or if your DUT will ever reach the temperature setting. It may sound like heresy, but these tests only have limited use in the real world, in our opinion, and can give you a false sense of security about the temperature at your DUT. There are quite a few reasons why the DUT temperature is different from the temperature at the air control sensor. The air sensor may measure the desired temperature setting, but the chamber walls, the insulation in the walls, and the chamber window are still hotter or colder and needs time to stabilize. In the meantime, the DUT itself has mass and takes longer to stabilize than the air around it. How long does it take for my DUT to stabilize? Well, that's hard to predict. We would need to know the thermal characteristics of the material it's made from, its weight, and the exposed surface area. You would really need to have an independent temperature sensor attached to your DUT to characterize it. The temperature controller begins to throttle at around 5 degrees before the temperature setting. This function is called proportional band. This is analogous to putting your foot on the brake before you reach a stoplight. This adds to the lag in time between when the air sensor measures a particular temperature and your DUT actually reaches that temperature. This graph shows the region where proportional band begins to take effect. There is always a tendency for the temperature to settle below the temperature set point in any proportional system, so this droop is compensated by the reset or integral parameter in the controller's algorithm. This graph shows how the part temperature lags the air temperature. You can see where the proportional band region adds the lag in a big way. In this real-world example, the part temperature settles 1.5 degrees C lower than the air temperature set point of 85 degrees. The long time to settle results in longer than expected test time. Plus, the test results may not be valid because the DUT never reaches the exact temperature set point. So with air control only, you need to add time. This graph shows a temperature profile with steps from 85, 50, 23, 0, minus 10, minus 20 degrees C, and then back up in the same increments in our Model 155 temperature chamber. The profile soaks at each temperature for 30 minutes before advancing to the next temperature. As you can see, the DUT never quite reaches each temperature step, even after the air temperature has been stable for 30 minutes. With air control only, you would need to add additional soak time at each temperature to ensure that your DUT reaches that temperature. To get accurate results with air control, you would need to characterize the process by measuring your DUT temperature independently. It might take minutes or even hours longer for the DUT to reach the desired temperature than when the chamber's temperature controller indicates you've reached a set point. In fact, the DUT may not ever reach the desired temperature. This characterization is an iterative process and will be different depending on the DUT and loading in the chamber. Of course, the consequence of not characterizing the temperature at the DUT is false data. But there is an alternative, Cascade Control. Cascade Control is the technical name for a two-loop control system where the air temperature, or inner loop, is determined by deviation of the part temperature, or outer loop, from its set point. With Cascade Control, the air temperature is biased higher or lower in a precise manner for the fastest response at the DUT. Test equity uses deviation cascade control mode. The air temperature is allowed to deviate by up to plus or minus 15 degrees C from the part temperature set point. The air temperature is lowered as the DUT approaches set point in a precisely controlled manner. With this method, the DUT is never in danger of going to the maximum deviation temperature. This graph shows how the air temperature is controlled to overshoot or undershoot in a precise manner with Cascade Control to achieve the fastest response at the DUT. Here's a graph of the previous step test we saw a few slides ago. You can see how the air temperature is biased up to 15 degrees C higher than the DUT temperature, and the DUT reaches the desired temperature well within the 30-minute soak time. Here's a look back again at the air control graph. Big difference, isn't it? As stated earlier, Cascade Control can give you shorter test time and more accurate results, but there are some potential downsides that you should be aware of. The part sensor must always be attached to the DUT at all times. If the sensor is not attached to a DUT or dummy load, the air temperature will be unstable unless Cascade Control is disabled. There are also some issues if your DUT is dissipating heat. Your DUT may normally have a rise in temperature over ambient. If the case temperature is always, say, 10 degrees C over ambient, and you are using Cascade Control, you may want to set the temperature 10 degrees C higher. For example, if you want to test at room temperature of 23 degrees C, and the 10-degree rise equals a 33 degrees C case temperature, you may want to enter a set point of 33 degrees C. In this instance, you will precisely control the case temperature to its expected value at this condition. This will still result in shorter test time and more accurate results. Here is an example of how the F4T touchscreen controller appears with Cascade Control enabled. The air control button is not on. The temperature display on the left side is the DUT temperature. The air sensor display on the right side is the air temperature. In this mode, the part sensor must always be attached to the DUT. Keep in mind that Cascade Control is an option which needs to be specified at time of sale, and the standard F4T controller does not have this capability. You can disable Cascade Control on the F4T by pressing the air control button. Notice the green check mark on the air control button, which indicates it is in this mode of operation. In air control mode, both displays indicate the air temperature, since that's what's being controlled. You do not have to attach the part sensor to anything when air control is enabled. There is a third mode of operation on the F4T controller with Cascade option. In the controller's loop menu, there is a setting called Simple Set Point Enable. If you turn Simple Set Point Enable on and leave air control off, the chamber will operate in air control mode like a standard chamber. If you have a guaranteed soak step in a profile, the step will not begin timing until the temperature on the part sensor is within a predetermined tolerance band of, say, plus or minus 3 degrees or so. Or in a wait for process step in a profile, the step will not begin timing until the temperature on the part sensor is at a predetermined temperature setting. In this way, you are only controlling the air temperature, but using the dot temperature to determine when the step begins timing out. At the same time, you are monitoring the dot temperature, which can be recorded using the F4T's built-in data logging feature. Our new Model 155 benchtop chamber includes the F4T and Cascade Control as a standard feature. The F4T touchscreen controller without Cascade Control is a no-charge choice instead of the original F4 controller with arrow keys on all other temperature chambers. Adding Cascade Control to the F4T is a $375 option when purchased with the chamber. We have a retrofit kit for older chambers. We have thousands of chambers in the field since 1998 that have the original F4 controller with arrow keys. They can be upgraded with an F4T touchscreen controller and Cascade Control for about $2,200. The controller can be easily installed by anyone who has moderate mechanical skills. Cascade Control is only available for temperature chambers. It is not appropriate for humidity chambers because humidity and air temperature are inextricably linked. You cannot have stable humidity control if the air temperature is not fixed. Thank you for attending this webinar about the benefits of part temperature control, also known as Cascade Control. Feel free to ask questions at this time.
And once again, ladies and gentlemen, if you would like to submit a question, please do so.
Okay, hello. Thanks for attending everything, as I said before, and I see we have some questions that I'll try to answer. One person asks, he says, your 1 pound static load would vary greatly depending on the surface area of the object. What state did you use for your stand-in dot? Well, in that particular case, it was a cube of aluminum that was 1 pound. If you use any other kind of shape, the control dynamics would still control in a similar manner. In some cases, the tuning value for the part control loop might have to be changed to optimize the response, but it's still going to be a lot better than using air control only. And you should be able to achieve similar results with any kind of load that you would put in the chamber. Someone else asks if we have any plans for more seminars in the future. Yes, we will. We'll be doing that at least every quarter moving forward, and maybe sooner than that, depending on production time. Another person asks, how do you attach the sensor to the dot? That's a good question. I omitted that in the slides. So the part sensor is one of 2 ways. It's either a open bead thermocouple, which is what we provide in the majority of cases, and in the Model 155 chamber, it's an RTD sensor that has a metal tab on it with a screw for a hole. So in either case, you can use something like aluminum tape or any high adhesive tape, tape which can respond to high and low adhere at high and low temperatures to your dot and just tape it onto the dot, or you can put it under a screw and washer to hold it in place. There are more exotic ways to do that with. There are epoxy adhesives that could be used that have thermal properties, thermal conductive properties, where you can attach it to your dot in that manner. Someone else asks about the does the chamber have an external interface, and what's the message protocol? So the F4T controller has RS-232 interface and an Ethernet interface. Both of those interface uses the Modbus protocol. However, the Ethernet interface can also accommodate SCPI commands. The new version of the firmware includes SCPI commands for Cascade Control mode that was just released earlier in the month. So we can now send SCPI commands easily over the Ethernet interface. There's also an option for a GPIB interface, which is essentially a GPIB to Modbus converter. And there's a lot of magic in that box that's behind the scenes. And it takes care of the Modbus programming protocol and converts the commands to simple ASCII-type commands for read and write commands. So that would be an external box that plugs into the serial interface to provide GPIB capability. Let's see what other questions. Someone else asks if slides are available. Yeah, we'll have a link on our website to download those slides, and they'll also be. We recorded this presentation as it happens, so we were able to. We will have a YouTube video of this presentation with the narration behind it. Let's see what other questions we have. Okay, someone else asks if we have an API for LabVIEW. We don't have any LabVIEW drivers at the moment, but it's pretty easy to develop your own, especially if you're using the SCPI commands. Okay, some of the other questions that we have here. I think that's all the time we have now, and I have some other questions. I'll try to answer them in on the website that has Cascade Control information. So if you go to www.testequity.com/cascade, that will have information about the Cascade Control and some more downloadable content. And if you want general information about the F4T controller, it's testequity.com/F4T. Okay, thank you all for attending, and hope to see you in the next seminar that we do.